Hi, I'm Dave Farley of Continuous Delivery and welcome to this special compilation episode. This episode covers my most important tips for working with microservices. This month we're producing a series of these compilation episodes to manage our workflow at Continuous Delivery to make sure that we can keep producing great content and stay on top of our other projects away from the channel too. But we didn't want to leave you empty-handed, so we thought this would be a good way of keeping you satisfied until we can return with new fresh content. Before we get to the first clip though, let me thank our sponsors. We're very fortunate to be sponsored by Equal Experts, Transfic and Tuple. Equal Experts is a multinational consultancy built on applying the ideas and techniques that we talk about here to build great software for their clients. Transfic is a financial technology company applying advanced continuous delivery techniques to deliver low latency trade routing services to some of the biggest financial institutions in the world. And Tuple builds software to make pair programming easier for people who work remotely. All of these companies offer products and services that are very well aligned with the topics that we discuss on this channel every week. So if you're looking for excellence in continuous delivery and software engineering, click on the links in the description below and do check them out. Now that's out of the way, I hope that you enjoyed this episode and I hope to see you again soon as well. A microservice is defined by these properties. They're small, focused on one task, aligned with a bounded context, autonomous, independently deployable and loosely coupled. I think that the first thing to notice is that this says nothing at all about technology. Nothing to do with REST APIs, for example. The next elephant in the room here is independently deployable. I've covered this aspect in the past, but I think that this is the defining characteristic of microservices. In fact, if you look at this list, all of these ideas are aimed at helping us to achieve that independence of deployment. If you and I can't develop our services independently and then release each of them without needing to test them together before that release, they aren't really microservices and they certainly aren't independently deployable. So that's quite a tough design challenge. If that is what we need to achieve, how do we go about it? Well, I think that the most common starting point for teams adopting microservices is actually the wrong one. That is, setting up a separate repository for each new service. The problem here is that defining interfaces between the services that you can rely on to be stable enough and loosely coupled enough to give you enough protection so that you can change the behavior in one service without compromising the interface that others depend on is very difficult. You're almost never going to get that right the first time. Forgive me name dropping, but I was talking about this idea recently with my friend Eric Evans. Eric pointed something out that was a consequence of my approach, but that I hadn't thought of in these terms before. The language or protocol of the information that we use to communicate between the services is a separate bounded context. Let's imagine a small group of services. Our aim is for these things to be independently deployable. They need to talk between one another to do useful work, so of course they are coupled to some degree. They're coupled through the conversations that they have with each other. So if we want them to be loosely coupled, then the nature of those conversations is very important. Certainly we'd like them to not be too closely tied to the implementation of any one of these services. This idea of these conversations representing a separate bounded context resonated with me. It helps me to better understand why my approach to microservices works for me. So, some ground rules before we explore this in a bit more detail. Bounded contexts are a big idea. They were introduced in Eric's book, Domain-Driven Design. The idea is that multiple models coexist in big software systems. A bounded context is an area of the problem where one of these models is consistent. If we are building a bookstore, then the bits of the store showing the books for sale and the bits of the store responsible for, say, shipping the books both have the concept of book, but those concepts are different.
The books for sale probably need some cover art and some samples of the contents and that kind of thing. The shipping part probably needs to know the weight of the book and the destination address, but doesn't really care about the pictures or the text. That's because these are separate bounded contexts, separate models of bookness, whatever that means in their context. It's a very good idea to always translate ideas that cross the boundaries between bounded contexts. The alternative is that you have to establish some kind of grand one model to rule them all data structure that works in every possible context. This is close to, if not impossible, and even if you did manage it, then every single change to the model would break everything. So this is a really bad idea. Much better to follow the advice and translate between contexts. Remember our definition of microservices. One of the items says aligned with a bounded context. So what this means is that every time two services communicate, there should be a translation between the concepts that they exchange at the boundary between them. I've talked about this before in a previous video too. If we think of the messages that we exchange with that information with as a distinct bounded context in the way that Eric suggested, then that means that we should translate to the message and from the message. There are some little bit of code that acts as the insulation between our services and the messages that it sends and receives. This is how I've built distributed service-based systems for years, but I hadn't really thought of it like this before. The key idea here is that we either want our messages to be more stable, to change at a slower rate than the services that produce and consume them, or more independent, to be able to change without forcing change on the services. This little translation layer helps us to achieve either one of those things or both. And the idea of the messages representing a distinct bounded context helps to guide us towards some better answers as to how to achieve that. The first problem then with a microservices system is which pieces should we define as services? And then the next, which follows very quickly afterwards, is how do we establish these magic messages that are durable enough and loosely coupled enough? We're looking for good abstractions here. And the best approach to finding good abstractions is to iterate. Create your first guess, try it out, see how it stands up to real use, and then refine it as you learn more. So my preferred approach to creating a microservices system isn't to begin with microservices. Before I get there, I need to be able to iterate quickly enough to learn about the problem. Only then can I abstract it so that the messaging context is reasonably stable. We don't need some elaborate whiteboard exercise, but it will certainly be handy to think about the problem a little bit, to play with models of it so that we can try out and find our first guess at services and messages. My preferred approach to this part these days is event storming. There's a link in the description if you'd like to learn more about that. But we also need to write code, live with it for a little while, and see how it works out as our understanding of the problem that we are solving and of the system that we are building deepens. Only then will we know if our design works to insulate our services from change. During this phase, I want to minimize the overhead of changes. As soon as any of my services live in a separate repo, there's a significant overhead involved. If I change service A, and that requires me to change the messages and so change service B, then I have to work in repo A, switch to repo B, run continuous integration in each, coordinate the versions to see if they work together, etc., etc., etc. If service A and service B were in the same repo, if all of their tests ran in the same continuous integration cycle, if their releasability was determined by the same deployment pipeline, I get much faster feedback. I can make my change to service A, to the messaging between them, and service B in seconds. I can evaluate them all together for releasability in minutes. Continuous integration gives us the clearest, most definitive feedback, and it works even when our solutions are relatively tightly coupled. So we can start off with our best guess of a good design. Separate services interacting through ports and adapters, perhaps, with our current best guess of that messaging context. But we can use continuous integration and continuous delivery to evaluate all the pieces of whole systems or large subsets of systems together in one pipeline. This is dramatically simpler at this stage if everything is stored in one repository. This is the simplest way to get to a definitive statement of the coherence and so releasability of our system. Work like this for a while and evolve the messaging until it doesn't change very often. Now, pull out services as microservices based on messaging that you know works and store them in separate repositories. The risk of this approach is that it's easy for a developer being careless to ignore service boundaries within the bigger scoped repository. So you need to adopt a little bit of care to keep these service boundaries clean. Maybe add some tests that reject changes that try to share code that worries you across service boundaries. Despite this risk, I see this as a much better alternative to premature decomposition of services and repositories. I think that an extremely useful way to think about this is in terms of its deployability. I describe a deployment pipeline as a mechanism to determine the releasability of our software. That means that within the scope of a pipeline, we need to be able to establish a definitive answer to the question, can we release or not? So the correct scope for a deployment pipeline is an independently deployable unit of software. At the start of your project, when you don't yet understand the problem really, you don't know which services make sense, and you don't know which messages will be stable in the face of the evolution of your system, then you can't confidently release the pieces without testing them together. So bung everything into a single repository, evaluate it in a single pipeline shared between teams, but still architect your systems around services. And try and keep your services independent and nicely modular. Later, when you've learned the answer to these questions, you can pull things apart. The problem is that as soon as you care whether version 7 of service A works with version 15 of service B, you have a dependency management problem. And you don't have independent teams working on services, you have a monolithic team working inefficiently in a bunch of separate repos. This is a more complex solution. I was pleased when Eric described the messaging as a separate bounded context. It helped me to rationalize my thinking. But on reflection, I think that there's a danger that it might be slightly misleading too. So I want to clarify that. The risk is that we see it as a single bounded context. And then there is the danger that we're back in the one message to rule them all world. I see this as more of a collection of bounded contexts, really, clustered around different conversations that might be going on in the system. For example, I don't need every different message that talks about books or whatever else to have the same representation of a book. It's conceivable that there are subgroups of conversations going on, but it is more complex than that too. For big systems, you'll probably certainly need the ability to subdivide the conversations this way, but you also need to be able to correlate the conversations in different contexts. So we'll need to be able to tell that the conversation about my book shopping book is talking about the same book and the same customer as the other conversation that talks about shipping it. We sometimes need some common ideas that transcend these bounded contexts in our messaging domain and allow us to glue the information together. This is another common problem that people creating microservices sometimes struggle with. How do we, on one hand, create independently deployable services, but services that can also work together to create a consistent, traceable picture? To address this, there's another model, another layer in our abstractions. At the base, we have our services. Next, we have the messages and the message contexts. And then on top of this, we have another model. This model of core concepts in our problem domain that glue everything together. This is usually very simple. In the olden days, we might have talked about key entities in our systems or something like that. These are the things that you need to be able to search for, to look up, to maintain the history of, and so on. The customer accounts and books in our bookstore, perhaps. Our lives will be easier if these things have a unique ID that is durable across contexts. It will allow us to stitch the conversations together. Sure, you can translate these IDs on the way into a service on the way out, but this kind of makes traceability a little bit more difficult. Let's be clear, you can't always do this, but if you can, it does make life easier. This collection of IDs or keys kind of hovers above the messaging context, and it should intentionally be simple, as simple as you can make it. The good news is that these things are usually pretty obvious when you look at the problem. They're the top level ideas that flow between bounded contexts. My preference is to try and model all of the conversations that the messages represent at the level of the problem domain, a kind of technical version of our ubiquitous language for our system. This helps us a lot with the messaging and the top-level entity abstractions. If we get this right, then a non-technical person who understands the problem should be able to understand the conversations that are happening between services. They may not understand every last detail of every message, but the broad brush picture will be accurate. So we will have messages like order book, dispatch book, and book dispatched that contain books and customer accounts and not much else. We'll avoid technically focused messages. This reinforces the bounded context idea of our services, and one of the big advantages of that is that bounded contexts are often naturally loosely coupled with respect to one another. So our services will also tend to be more loosely coupled too. So, my advice is to work iteratively to design the conversation between our services. Assume these conversations will be in the language of the problem that we are solving, not focused on the technicalities of how we solve it. And when you need to iterate fast so that you can learn fast, breaking things up too soon gets in the way. Microservices are a very good strategy for building big systems with lots of people. But they come at a cost. They aren't a great idea for simpler systems or small teams because of these costs. So what are the costs and how do we address them? In particular, how do we design and test microservices if we aren't allowed to test them together before we release them? Let's just recap this constraint and why it's fundamental and matters. Microservices are an approach that is designed to optimize for team scalability. They are for bigger teams, so that these teams can divide work up between smaller, more focused teams, and still make useful progress. The problem of dividing teams up like this is the coupling between them and their software. If I write some code in my service that changes how it's used, and your service depends on my service, then I may have broken your code. If I want a new feature in your service that allows my service to do something new, I'm tied to your team in some way unless I work to avoid it. I can either guess at how your change will work and code for my guess, or I can wait until you're done and now your team and mine are working in lockstep, unless your API is backward compatible with the previous version. We are coupled together and can't make progress independently. Both of these cases are a problem of coupling, and in big organizations are a very big deal because this coupling compounds. My team's blocked on yours, your team's blocked on Jane's is broken by a change somewhere else, and so on and so on. The State of DevOps reports say that one of the main predictors of high performance in teams is their ability to make progress independently of others. Microservices was designed to alleviate that problem. Let's be very clear. There's nothing fundamentally new in the idea of microservices, but this independent deployability is the closest to a new idea in practical terms. Let's get back to our two services, yours and mine. and the two ways that they can be coupled. I can break your code changing my service, and you can stall my development while I wait for a change. There are two ways that we can tackle these problems. We either accept that we must test everything together before release. This checks that I haven't broken your service and that our services are in step and can do useful work together. And for this to work at any sensible scale at all, what we need is fast, efficient, high quality feedback. So that for this scenario, microservices are a fairly dumb idea. We don't want barriers between our services that slow us down. The easiest way for me to see that I've caused a problem with your service when I change my service is in a continuous integration and a shared repo. We put both of our services together in a single repository, practice continuous integration, and get near instant feedback on whether our changes work together. Similarly, if I need a change in your code to help my service do something new, the easiest, most scalable way to do that is allow me to make the change for myself when I need it, rather than wait for you to schedule it. So again, shared code ownership, single repo, not really microservices. But there's another approach, and that is the microservices approach. For this, we're going to accept the challenge that independence of deployment presents and be willing to pay the costs in terms of a bit of extra work and a bit more sophistication in the design needed to achieve it. What this demands of us is really two things. We need to design APIs that are loosely coupled and APIs that we can defend. This is where the ideas of microservices being aligned with a bounded context and being independently deployable really come from. Interfaces between services should be abstract. It's important that they hide implementation detail so that implementation can change. Another benefit of microservices is that they should be easy to replace with better versions. So we don't want the detail of how they work inside leaking out. Aligning them with a bounded context helps with all of this. But the other part of the technicalities of dealing with the boundaries between bounded contexts is that you should always translate at these points in communications. Ports and adapters is a really good design idea at these points to provide a bit of helpful insulation between our services and a place in your design to cope with changes more easily. We'll come to that later. So now we have a service. It has a well-defined API of some kind, and it only interacts with other services via their well-defined APIs. These APIs could be anything. No reason at all why they should only be HTTP. That's not in the definition of a microservice. Perfectly valid to have a microservice that consumes or publishes binary data or anything else. But tagged data formatted messages can help, but we'll get to that. My preference is that services are message-based and asynchronous. I think that makes our life easier, but this is still just my preference. Nothing in the definition of microservices said that they must be. Let's imagine I want to create a customer registration service of some kind. It allows me to register new customers. So here's an add customer message. It contains a customer name and an address. And in response, it generates a customer added event that contains a customer name and a unique ID that's been generated by our service. I could have chosen to include the address in the response, but by doing that, I'm coupling the idea of customer to the idea of address. I know from painful experience that addresses can be quite annoying sometimes and that we may want different things from them at different times. So this is something that I expect to change, so I'm going to separate that out in my design. If someone wants to ask my service for a customer address, that's fine, but we'll deal with that separately. This is a separation of concerns decision. I've decided that services that are interested in new customers probably aren't always interested in their addresses. Not saying that this is always right, merely that by making this choice, my design is a little bit less coupled, or at least the coupling is a little bit more discrete. When I store my new customer, I could just take the incoming message and process and store it as a blob. When somebody asks for a customer, I simply send them the contents of the blob from the store with no translation. That's not a very good design. It may mean that my service was simple to write, but it's now also fragile. If I want my service to evolve, there isn't really very much that I can do here because every consumer of my service is now coupled to how I've decided to store its data. There's no abstraction, there's no information hiding of any kind. This is actually quite a common form of service in teams that are trying to move to expose information from legacy systems, for example. They will often write a service that simply passes on some blob of data. So now consumers are coupled to the service and their implicit understanding of the structure of that data. The service isn't really going to do very much work. It's certainly not reducing coupling. A service, or actually any module or class or function in our code, should keep some secrets, otherwise what's the point? In our example, we have two ideas, customer and address. We've already imagined that addresses may be slightly slippery. What if our business is successful and now, as well as addresses with a UK postcode, we decide we'd like to add support for German or US addresses as well? If a UK postcode is implicit in the data structure that we expose, there's no option but to force on all of our consumers of our service that we want to add US or German addresses. The boundary, the API of our service, is a special place in our design, or it should be. It represents an integration point, a designed point at which our aim is to reduce coupling. That's why it's an API in the first place. This is particularly true for microservices because if changes here force changes on others, that's a big deal. If we don't test them together before release, we could break other people's code that way, or maybe even the whole system. So how do we gain the ability to change our microservices safely? The first thing to think about is the information that we expose and how we do it. What does our API look like to a user of our service? What implementation detail secrets do we want to keep within our service, and how do we keep them? Our primary goal with the design of our interface is to expose our best guess of the minimum that our users of the service will need to understand to use it. Don't add lots of extraneous detail. Keep it as simple as possible and as focused on the service that you provide as possible. Don't add stuff to the interface just in case, or just because we have it so we might as well. Actively design the interface to be simple and minimal. Then present that interface in a way that, as far as we can guess, is likely to continue to make sense in the future. We won't get this right, but recognizing that it would be good if we did makes us try just a little bit harder for a decent abstraction now. This is part of how you build a more loosely coupled interface. The other part is how you organize the information and access to it. Let's go back to our customer and address. We could decide to adopt a fixed binary format for our messages. The first 2 bytes are customer ID, the next 100 bytes are the customer name, and the next 200 after that are the customer's address. Everyone that uses addresses now needs to understand this fixed structure. Clearly, this is far from loosely coupled. Later, we realise that if we end up with more than 1,024 customers, this design breaks. So we decide to increase the customer ID to 16 bytes instead of 2. This change breaks our user interface with every user of our service. We could improve things by making it a class and hiding the detail of the structure of the data inside it. This is a small step, but it's a step toward looser coupling. Our service users still need the correct version of the class to send or consume the data correctly, but at least they aren't worrying about byte count anymore. We could abstract this a little bit further. We could add an interface instead of a class. So now we could plug in different implementations beneath the interface. This represents a contract that we are using to manage the conversations between us. We could imagine adding some kind of version number to different implementations of our contract, and then our service, if it was sent an old version, say one that stored IDs in 2 bytes, could upgrade the incoming information into a usable form that the latest version of our service needs. We still have some problems though. Things are getting more complicated for our service now. We've now got two classes of users: early users who have IDs that can be stored in 2 bytes, and later users whose IDs can't. So we either need to keep supporting both groups, or we need to migrate everyone to the new version. In a real microservices world, you don't get to force changes, at least not in lockstep, on other people. So we must keep the old version and the new version of the APIs working alongside one another, at least for a while. So now we have extra complexity added to the design of our service to keep our system stable overall. Okay, so most of you probably aren't worrying about bytes and byte order, but do you expose a file format or a data stream from, I don't know, a hardware device or a legacy system direct through your API anywhere? Does your service or the code of your consumers need to understand the data structure or file format? Because if they do, you may well be concerned about bytes and byte order after all. The reason that most teams don't need to care is because they've taken another step up the ladder of abstraction. They use more dynamic data structures like XML, HTML, JSON, YAML, and so on. These are often tag delimited forms. They're horribly inefficient for ways of sending data, but having the tags means that now we know what each piece of the data means. Now we can depend on the tags rather than just the position of the bytes. This allows us the freedom to shift things around. If I have a tagged form of my customer and address like this, I can easily add a telephone number. And as long as you don't care what order my tags are presented in, when you consume them, you don't have to assume that you must consume every tag. Then your old code that knew the previous message structure will continue to work with my latest changes. This is another form of loose coupling. So what is the contract, the interface, the API to our system? It's clearly more than only the functions that we invoke to initiate the behavior that we want. It's more than add customer, because we publish information too. So it certainly includes customer added and maybe get customer address. Our contract is also the data that our service publishes that represents a customer, their address, their ID, their telephone number, and so on. All this stuff is externally visible and so represents the contract to your service. Changes anywhere here can break communications with other parts of the system. If our service is a genuine microservice, then these are the only places that can break interactions, because all interactions happen through these interfaces. So this is the goal, the scope of contract testing. Our aim is to confirm that we haven't broken our contract with our external users. We'd probably want to evaluate adding a customer and validating the response. To start with, that's probably all we'd need. Later, we'd want to find a customer with an old ID and one with a new one. Later still, we'd add a German customer and a US customer perhaps, and confirm that their addresses are supported correctly when we ask for them. And later still, maybe that we still get a response when our system was down and later came back up. When we run our contract tests, if nothing changes, then great. Our changes can't break anyone else, unless our abstraction leaks in some other way. If one of our contract tests fails though, we may have a real problem. So the aim of contract tests is to exercise the surface area of your interfaces with the outside world to spot any changes. This surface area includes the data that you expose that consumers need to understand. If a test fails, stop and think, is this an innocent change like adding the telephone number? In which case, as long as communication protocol that we are using between services isn't positional, then it's probably safe to change. Is it a breaking change for some people? Users who used to have 2-byte IDs can't see IDs with more than 2 bytes, in which case we'll have to do more work to insulate these users from change. We could keep supporting the old 2-byte API, but encourage them to update. Then, when they finally do, we could retire the old API perhaps. Maybe we keep an old and new version of the service running in parallel. Or maybe we implement support for different versions of the API in our new version of our service. Finally, there may be changes that for one reason or another are going to force change on users of the service, whether we like it or not. Now we'll need to go cautiously. Remember, we can't force change in lockstep on our users. We may not even know who our users are. So now we will have to support old versions of the API and communicate with users or people who may be users to let them know of the upcoming changes. We may need to do old school stuff like run a beta programming and support external testing some way. One more thing before I wrap up. I think that recognizing that the interface to your service or system is everything that is visible to the outside world is an important idea. It's not even just all the externally visible data as well as all of the externally visible functions. The operational characteristics of your system or service matter too. This starts to move in the direction of reactive systems, which I cover in more detail in this video. But the idea of the contract of our service or system is not as simple as the functions in an interface or the collection of messages that it responds to. It goes a bit deeper than that. These are the problems of supporting external APIs, and the value of microservices is built on that idea of supporting external APIs.
In this episode, I want to explore the problem with microservices, and particularly why this very valuable architectural idea is probably not quite what you think it is. It's simple, right? Microservices is all about small services, isn't it? No, not really. The first problem is that microservices is a distributed systems architecture, and however you wrap it up, distributed systems are way more complicated than non-distributed systems. There are all sorts of problems that you just automatically buy into when you start distributing computing across multiple different devices. One of the things that microservices are not services with simply a REST API. That's another thing. That's REST. It can be implemented as a microservice or not. REST may be a useful technique in implementing microservices or not. There are many different ways of approaching this, but a RESTful API does not define a microservice. And all services are not microservices. Services as an organizing principle for software systems has a very long history. We'll talk a little bit more about that later on. The defining characteristics of microservices are that they are small, as we've already mentioned. They're focused on accomplishing one single task. They're aligned with the bounded context in the problem domain. They are autonomous, independently deployable, and loosely coupled. Let's talk about each of those ideas in a bit more detail. So what does small really mean? Everybody asks this question, and it's kind of an obvious question from the name, right? Microservices, so what does micro mean? There is an answer that comes from the early pioneers of microservices, which is that a microservice fits inside of James Lewis's head. James was one of the people that first popularized the idea of microservices. He, along with Martin Fowler, wrote the first article that was published, I believe, online, or at least the best known article that describes them in more detail. And James, as you can see from this picture, has a reasonably large head. He's a smart guy, so a fair amount fits in his head. But the idea is to make them understandable, to compartmentalize a problem so that we can deal with it and understand what's going to happen. A reasonable rule of thumb to try and figure out how small is small or how micro is to imagine throwing away your microservice and re-implementing it. How long would that take? If you can do that in a few days or maybe a couple of weeks, it's probably on the right kind of scale. If the idea scares you of throwing away the service and rewriting it from scratch, it's probably too big. The next in the list is focused on a single task and doing it well. This is really about separation of concerns, but at the level of the problem domain. What we're really trying to express here is the idea that a microservice accomplishes one task when viewed from the outside. Now, implementing that task may involve a bit more concerns perhaps. Maybe you're thinking about storage or getting data from another source or something like that. But from the outside, the service is going to be focused on accomplishing one task and achieving that well.
The next in the list is aligned with a bounded context. Most teams miss this idea, and it's an important one. A bounded context is an idea that comes from domain-driven design, the fantastic book written by Eric Evans, which describes modeling the problem domain as an approach to designing the software. And one of the things that Eric talks about, one of the key ideas in domain-driven design, is this idea of bounded context. Eric defines it as a defined part of software where particular terms, definitions and rules apply in a consistent way. This is a part of the problem domain where the concepts are related to one another, and so it makes a cohesive unit. This is an important idea in lots of different contexts, but in the sphere of microservices, it's a very important idea because those are the boundaries that we would prefer to align our services with. And this is important for several reasons. First, if we break a problem, a monolithic application, say, into a collection of smaller technical services, that doesn't really qualify as microservices. They are not aligned with the bounded context, and you're going to suffer from increased coupling between those components. Bounded contexts are kind of like natural fire breaks in the problem domain. They are, if we align our software with those fire breaks, then it means that our system is going to naturally be less coupled because the problem domain is less coupled at those points. And so it means that we can write cleaner interfaces to our services and have less chatty interactions between them. One of Eric's pieces of advice in the domain-driven design book is that whenever you transition a bounded context boundary, then you should translate ideas, information that crosses the boundary. That means that every microservice should be translating its inputs and translating to its outputs in order for every interaction. A microservice should always make a break between these points. We should make a significant distinction between the external protocol with which the microservice exchanges information with other parts of the system versus the internal representation of that service and the model within. We need to really treat seriously the difference between the design of those APIs, those entry points into our services, and our consumption of those APIs from other services. If you aren't using ports and adapters in your implementation of microservices, you're probably making a big mistake. We want to always be translating at these points. The next in the list is that microservices are autonomous. The teams that look after these microservices can make progress alone without the need to interact with other services or other teams. I can change the implementation of my service without needing to coordinate with anybody or anything else. This is the biggest value of microservices. This is the thing that allows microservices to work in organizations that scale enormously. But it's also the most commonly missed attribute of microservices. What I see frequently is teams claiming that they're implementing microservices, but building, testing, and deploying all of those pieces together. That's something else. Let's explore this idea for a moment of autonomy. Service-based design is not the same thing as microservices. Service-based design has a long history. It's been around for a very long time. If you'll forgive me, I'm a bit lazy and I haven't looked up the history of service-based design, so I'm going to do this from a personal point of view and tell you my interaction with it. I've been building distributed, service-oriented systems, however you want to frame that, for about 30 years now. I started at the end of the 80s and 90s with my first foray into distributed computing. I moved reasonably quickly in the early 90s into ideas like remote procedure calls, and then quickly into an idea of something called object request brokers, where we were simulating interactions with component-based systems in distributed systems. I got involved in a startup where we built some infrastructure to support what we would now think of as quite advanced microservices based on a concept called cooperative business objects, little bundles of domain logic that communicated through what we call a semantic data service, a bit like XML, but predating XML. I then moved on bigger commercial systems, working on component-based systems, message-oriented architectures. Service-oriented architecture came in at the beginnings of this century and became more popular. And then I moved into building high-performance systems based on event-driven architectures, sometimes using patterns like CQRS, microservices, and ending up with something that we called reactive systems. All of these are service-oriented systems. All of these models were based on that concept of little bundles of logic that were somehow more discrete from one another than the classes and functions within our implementation, and so had more abstract interfaces between them. The ideas of service orientation are extremely useful. They're an important idea, I would argue, in computer science and building bigger systems. And I think that they principally matter for two reasons. One of those is technical, the other is organizational. Now, these are very closely related, as Mervyn Conway stated in 1967. Any organization that designs a system defined broadly will produce a design whose structure is a copy of the organization's communication structure. So the architecture, the design of our systems, is closely related to the communication topologies that we employ in the organizations that we work in. This has an impact on the kinds of architectures that it's possible for teams to build, and the architecture mirrors your organizational structure. If we decide to divide up our teams on technical boundaries, we have a UI specialist team and a middleware team and a data team, then we're going to build a system that looks a bit like this, a tiered, layered system, and the teams will have to coordinate and interact. More modern software development approaches tend to prefer smaller, more autonomous teams. If we're going to, for a variety of reasons, if we are going to organize ourselves along the lines of more modular, autonomous teams, we're going to build more modular software with more autonomous components, and it looks like this. But this is not necessarily a microservice organized system. We could choose how we were going to organize our teams around this. We could put everything into one big repo and have a distributed service-oriented system communicating with REST or messaging or whatever other technique. Or we could have independently deployable units of software, autonomous components that were microservices. They're not the same thing. So if we can have distributed monoliths organized as collection of services, which is probably my preferred architectural approach, if I'm honest, for many systems, what does microservices add to that? Well, the key thing is that they are independently deployable. Deployability is one aspect of autonomy for these services, but it's an incredibly useful one. If we can work on changes to our service and deploy it without necessarily communicating or interacting with other groups of people, that means that we can make progress without being constrained by those groups. It means that we are developmentally less coupled to the rest of the organization. That's really what independently deployable means. If I need to care about dependencies on other services before I release my change into production, my software is not really independently deployable anymore. Well, this is a big idea, and this is the biggest stumbling block that I see with teams adopting microservices. And the biggest problem, the biggest cost of microservices. This has serious implications for the way in which we design software and the way in which we employ it. You don't get to test your services together before you release. You don't get to force changes that you make to your service on consumers of your service. You can't demand that they update in step with you. That's not part of a microservices model. If our services are autonomous and independently deployable, we build, test and deploy them independently. This is the real value of microservices. This is the step that decouples organizations both technically and culturally and allows them to grow and create software at an enormously fast rate. It's the thing that differentiates organizations like Amazon from more conventionally organized firms. And this is also the real cost, because if you want to be able to independently deploy these services, then you've got to be able to take the ability to maintain that independence really very seriously. Microservices are an organizational decoupling play. That's what they are for. If you don't need to decouple your organization developmentally, they're probably not the right thing to do because they come with this cost. They allow development organizations to grow very big and to work as a large collection of small independent teams. But to achieve this, microservices must be loosely coupled. We need to take that separation of external and internal representation incredibly seriously, and we're going to invest time and effort and development effort into keeping that separation clean. We need to treat the external interface of our services like a public API, because it is. We can't demand that other people change in step with us when we want to make changes to our API. So we've got to be very, very cautious about the ways in which we can change that API. When we're consuming the API from such a service, we should be cautious not to couple ourselves too tightly to it. We should only take the information that is of interest to us and no further. We'd like to make those interfaces as clean and abstract as we can achieve. So we should be very, very, very cautious of breaking changes at any point. It brings in techniques like supporting multiple versions of interfaces on the same service, or multiple versions of services in some approaches. These are the techniques of microservices. This is the cost of microservices, but for that cost you get some huge advantages. We need to create interfaces to our services that we can defend and rarely and only with great caution change.
Thank you for watching. I know that this was a little different to what you normally expect from us here, but I hope too that you enjoyed it all the same. Please do subscribe and like if you haven't already, and if you did enjoy the content today. Also, you might want to consider joining our Patreon members. Our Patreon members get lots of exclusive perks. There's also a lot of useful information on our training site, including detailed free tutorials as well as paid-for training in modern software engineering techniques. I hope to see you here next time. Bye-bye.